Alright guys, and welcome back to another day in the neighborhood. Alright, so today our notes are going to be on dating, relative and absolute dating, telling how old a fossil is. Alright. Alright, so we're going to start off. In order to use relative dating, or even absolute dating, we rely on something called the theory of uniformitarianism. Okay, so what this is the idea is that the laws and the processes happening today have remained unchanged throughout time. Present is the key to the past. So basically the idea is that all of the fundamental laws and all of the physics and science that exist today are the same science that exists in the past. If the amount of gravity that something has changed in the past than we have today, then that would result in a very different type of world. So uniformitarianism basically says that we have the same laws that we've always had in the past, and they haven't had any real significant changes that aren't still taking place today. And so this is the key to all scientific understanding, and as far as we know, it is mostly correct. There aren't really any changes in the fundamental laws of nature over time. This is as opposed to catastrophicism, which is an idea that used to take precedence back during the 17 and 1800s and the time before that. This idea, the Earth and the world, the universe was very young, and that catastrophic events caused massive changes. This idea has been revised, just like the idea that the world is flat. We've gained new information, and so we've learned that the Earth is old, very old, and experiences slow changes punctuated by certain catastrophic events, such as like meteorite impacts and floods and hurricanes and tornadoes. Alright, so in order to determine age, I told you we're going to use relative and absolute dating. So relative age. Relative age is placing geologic events in their proper sequence and order. So it does not tell you how long ago something occurred, but it does tell you the sequence. So A happened before B before C. So if I was looking at a bunch of different students and I said that Sally is older than Mike, I don't know how old Sally is and I don't know how old Mike is, but I can tell you that one is going to be older than the other. Now, if we have their actual age, if I tell you that Sally is 14, now we can start working backwards to figure out what age Mike might be. We don't know his exact age, we know his relative age. Absolute age is the opposite. So absolute age is when we can actually attach a number to something. We can say that Sally is 14 or that Bob is 12. The Battle of 1812 happened in the year 1812, or that a fossil is 45 million years old or something like that. So absolute age has an actual time number associated with it. And the way that we get this number, because no one was alive back then, no one could write it down, is by measuring the decay of radioactive isotopes. And this will give us a number that we can use to find the exact age. More on that in a minute. Alright, so relative age laws. So this is the principles that we use to tell us the relative age of something. The first one is the law of superposition. So superposition is the idea that in undisturbed sedimentary rock, the youngest layers are on top. Now, it does not apply to badly disturbed rock, so if there are significant changes like the ones we talk about in a second, this rule won't always apply. But in general, if you throw all of your clothes in a hamper, the clothes at the bottom of the hamper are most likely going to be the oldest clothes because you put them in first. Whatever you put on top is going to be the youngest. So when we look at sedimentary rock layers, like this picture over here, we can see that this freshly put layer right underneath the grass, this is the newest layer of dirt. As we go further and further down, we get to older and older dirt and eventually down to rock and things like that. Now, there's no way for young rock to get underneath here unless we've had one of the changes that we're about to talk about. Okay, so superposition. Here we see that as the sand and stuff has eroded down into this ocean or into this lake, we can see that it's put down different layers, and they have bands of different colors, like you can see here. So, for example, if we had a time period where there was a lot of rain and a lot of flooding, maybe we have a lot of darker mud. Or if we had a drier period where there's more dust and light particles that haven't been compacted together, those might be on the top. So if I find a fossil down here in this darker layer and I find another fossil up here in this whiter layer, what that tells me is that the one that's underneath it is older than whichever one is on top of it. And so by doing this, we can create a timeline of when different types of fossils existed. But once again, it doesn't tell us exactly how old it is. It just says, okay, this rock down here is older than this younger rock that's above it. All right. Now another one. So there are disturbances that can happen. The Earth is not always labeled with the youngest on top and the oldest on the bottom. Sometimes there are protrusions or things that come through it. This is the principle of cross-cutting relationships. Rock bodies are older than the events that modify them in any way. So in order for this dike, a dike is basically a bunch of magma that's pushing its way up through the Earth. So there was some magma and it's pushed its way up through these rock layers and it created a new layer of rock in between all of these. Well, in order for the magma to push its way up, these rock layers had to be there first. It would be impossible for a layer of rock to just kind of jut out of the air and then the rest of the rock layers kind of form around it. So what had to happen is the lava came through after these layers were already here. So that means that the dike is the youngest of these layers. So looking at this picture down here, this one's a little bit more complicated. All right, so A, C, and E, okay, A is younger, E is older, and then B is older than that. And then as we get further and further down, things get a little bit more complicated. So let's look at like this fault line here. So this line indicates an earthquake. Okay, this earthquake had to happen after layer E was already here. You can't break a rock if it doesn't exist yet. So E had to be here first before this D could have broken through it. Same thing with G. G has to be newer than B. Okay, so G can only come through this layer if this layer was already here. Same with all these layers down here below it. Okay, so cross-cutting is when a layer or something disturbs a layer that's already there. When that happens, the disturbance, like G or D, is going to be younger than whatever it's cutting through. Okay, inclusions. Okay, inclusions are fragments of another rock, okay, that are found inside another rock. So here we have some rock A that's included inside rock B. Well, in order for these inclusions to get into this rock, that means that A has to be older than B because it can't get stuck in the middle of this new rock if it doesn't exist. Okay, so once again, let me say that again. In order for something to get stuck inside a layer of rock, the smaller pieces that are stuck inside have to be older because if they didn't exist, there would be no way for them to get stuck inside the middle here. Okay, so once again, that's the law of inclusion. Now correlation. Okay, correlation is where we match up rock layers. So here we can see, okay, A, B, C. A is younger than B, B is younger than C, C is the oldest of this pile. But now when we're comparing it to this other rock layer, well, let's look at B and E. Well, which one of these two is going to be older? There's no real way to tell. They're both kind of in the middle. But look at layer B and look at layer D, and you can see that they have the same rock, and most importantly, they have the same type of fossils. We would call this an index fossil because it allows us to index or compare these two different layers. So we know that rock B and rock D are the same age. They're the same age. So E is older than D because it's underneath it. Oh, sorry about that, guys. So E is older than D because it's underneath it, and since these are the same, E has to be older than B. Okay, so once again, we know that these are the same age, we know that this one is older than this one, so it also has to be older than B as well. Alright, so looking at this picture, alright, so looking on the left side, this is easy. A is the youngest, okay, B, C, and then this one doesn't have a layer. Let's call that E, I guess. So this one would be C, with C is older. And then D is the newer one because cross-cutting, D cuts through all of these, including this fault. So that means that D has to be younger than this fault as well. Okay. So now comparing these layers here, okay, just like we did before in that little picture, we can see that these fossils here match up with these fossils here. So now we can compare the age of the rocks underneath them because we know that these two are at the same size. Okay. Now, unconformities. Unconformities are what happens when there's break in the records, usually due to erosion. So there's times when rocks can be worn away and they'll disappear from the rock layer. Now, at times, other new rocks may be put on top of it. So we've got old rocks, the youngest rock is worn away, and then newer rock is put on top of it. We're going to have a gap in between where that rock used to be. Alright, so here we can see deposition, something gets deposited. Tilting happens like because of earthquakes and tectonic forces, but then something wears it away, and we can see that the top area is missing, and then a new layer is put down on top of it. So you can see that we have these angled layers with these new layers on top of it. So these would be examples of unconformity whenever there's pieces of rock that are missing in our geologic record. Okay, this is just another example of that. So we've got our flat piece of rock. It gets compressed at some kind of convergent boundary maybe. Some water happens and it gets eroded and it gets worn away. But it doesn't stop the rock cycle. New rock is getting put down on top of it. And so when we dig down, we can see that there's areas where like this purple rock is missing. This would be an example of an unconformity wherever that rock is missing. So if I dug straight down here, I would see that the purple is missing. The law of faunal succession basically says that fossils occur in a definite invariable sequence inside the rock layer. So for example, you're not going to find a human skeleton underneath a dinosaur skeleton because dinosaurs existed before humans. If we did find that, that would be really amazing. Now, we're also not going to find any any dinosaur skeletons back during, the Precambrian time, which was back before dinosaurs existed. We're also not going to find any dinosaur skeletons up here in the rock layer because once they go extinct, we're not going to find those fossils anymore. So basically, all animals, all organisms exist during a specific time period. Now, they may exist for a very long time period, but they have a definite start date when they first appear and a definite stop date when they last appear, although that could be all the way up into the current. And so by using these records, we can kind of age when these creatures existed on the planet. Now, we talked about comparing different fossils. Okay, index fossils are a very important key to it. Okay, index fossils help us find the relative age of rocks. Now, in order to use these index fossils, there's a couple of criteria. First off, they need to live for a short period of time. So we talked about this the other day, that crocodiles have existed for quite some time, and so they basically would not be a good index fossil because if I find a crocodile fossil, they could have existed yesterday or they could have existed 50 million years ago. They also need to be found in many different rock layers in order for them to be useful. If they're only found in one place, then that won't be all that helpful. They need to be found over a wide area of the Earth so that we can be useful in comparing them against areas in, from North America to Africa, so we can compare the dates between different fossils there. They also need to be unique so that we can see them very easily, and when we see, like for example, this guy, oh, this is a trilobite. If I see a trilobite, I know that this rock is however many years old. Okay, so we're going to be talking about this another time when we go back there. Okay, we're going to be talking about this next, the geologic timescale. The geologic timescale was developed by placing rocks in their relative order, so it's basically like a timeline of Earth. The divisions are based on laws, changes in the fossil content, and unconformities. So like I said, we're going to be focusing on that maybe next week. Now, absolute time. Okay, absolute time is when we actually have a number for how old something is. So on the short term, one way that we can do that is by looking at tree rings. So if you cut down a tree, and you can count how many growth cycles it's gone through. Each of these dark lines is a winter. So starting here, this would be the first year, second, third, fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12. Okay, so this tree is about 12 years old. So by looking at the conditions for this tree, we can tell maybe there wasn't as much water this year, or maybe there was really good growth this year. There was really good sunlight and nutrients. We can tell that there was a drought or that there was a cold spell. So there's a lot that we can tell from tree rings, but it gives us an absolute age. If I find this tree, I can tell you that the soil that it's in is at least 12 years old or older. So I'm putting a number on it. But this doesn't really help us with fossils. In order to use fossils, we have to do something called radiometric dating. This measures the amount of time for half of a radioactive isotope to decay and form another type of isotope or stable element. The amount of daughter to the amount of parent equals the length of decay process, which equals the age. So this part's a little bit confusing. So in order to understand this, first off, we need to understand radioactive atoms. So let's say I have a uranium atom. Now, if it's a radioactive uranium atom, it is slowly decaying over millions of years, okay? And what will happen is a uranium atom, every couple million years, will randomly change. And we're still not even entirely sure exactly how this happens, but at some point, it will randomly change. It will go from a uranium into a radium atom or a lead atom. And when it does this, it puts off a piece of radiation, alpha radiation, gamma radiation, so it releases a proton or an electron or something like that. When this happens, a uranium atom will change spontaneously into a completely different type of atom, and it will release energy. This is how all radioactivity works, by releasing these energy, these particles, as one atom changes into another. Now, there's a set time that these changes happen on. So if I have a box of uranium over, say, 25 million years, half of that will change into another type of atom. Okay, so here's another one. So here we have some uranium that's changing into the lead, and the half-life is 1 billion years. I think they're just estimating there. I don't think it's exactly a billion. But anyway, after 1 billion years, exactly half of this uranium changes into lead. Now, after another billion years, another half of whatever's left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So half of 15, what is that, like 7.5, is going to change, and now we're left with 1, 2, 3, 4, 5, 6, 7, 8, right? So about 7. So of that 15 that was left, half of that changed. So now we're left with a quarter of what we had to begin with. And then after another billion years, we're going to lose half of that quarter. So we're left with an eighth, which in this case is about 4 uranium atoms. And so if I do the ratio of lead, Pb, to uranium, I find that it's about 1/8. Well, I know that in order to go from full uranium to 1/8 uranium is going to be 1, 2, 3 half-lives. I can tell you that this is about 3 billion years old. So uranium is just one example. We also use potassium, and then carbon dating is not used for dinosaurs, but it can be used for things that are more recently decayed. Okay, and so this is an example of carbon-14 dating. So here, carbon-14 is naturally made in the upper atmosphere by getting hit by the sun's radiation. This carbon-14 is eaten by everything that eats organic life, and if you're still living, the ratio of carbon-14 to normal carbon is a set amount. Now, once you die, you're no longer taking in any more carbon-14, and the carbon-14 that's there is going to start to decay. So by measuring just how much of it has decayed, we can tell you the last time that it started absorbing that carbon-14. But now it only works to about 20,000 years-ish, so once again, this doesn't work with dinosaurs, only with things like mammoths and, in the more recent time period. Okay, and then this is example of a geologic timescale. So we start with the raw data, we create a series of events, and so we know, okay, this is older than this, which is older than this, and then we assign dates to it. So if we know that this fossil is 50 million years old, well, now we know that everything above it is less than 50 and everything below it is more than 50. And then here, if we know that this is 20 million years old, we know that everything above it is younger than that, everything that's below it is older than that. So by using a combination of relative and absolute dating, we've been able to put together a time scale of how the world was during these different time periods. And so you can see that over here on the right. We can see things like volcanic eruptions and stuff. And so this is how we know about things that occurred long before humans were around to write about it. All right, so this is the end of our notes for today. You should have received a practice sheet. Make sure that you guys had finished with that. You also, I put a quiz in your Schoology. You're going to have a graded quiz on Wednesday. This first one is just going to be for practice. And then my class specifically, if you guys have not finished your reading guide, don't forget to get that done. As always, I'll be on Zoom if you guys have any questions or want me to explain anything. And I hope you guys have a great day. All right, bye.